Hey class, today we're going to go over chapter 4.6, variation of parameters. So this is a pretty useful method. I used it a lot through my time studying higher level math. Pretty useful. It's one of the more common methods of solving differential equations. It's very useful when we have coefficients that are not constants, but functions of whatever our independent variable is. Okay. Of course, we can do this when we do have constant coefficients, but it's a very useful method when they are not constant functions. Okay, constant coefficients. So what we're going to do is we want to put our higher order differential equation into standard form, meaning we want it to be monic. We want the first coefficient to be 1, so we would divide everything so that there's a 1 here. Then we have our function of x, and some other function of x or t if we're talking about time instead of position. Okay, so we're used to this from the linear methods that we studied in chapter 2, right? So what we're going to do is we're going to assume that my particular solution is some function multiple of the solutions to the homogeneous equation. Okay, so what we're going to do is we're going to assume that this is the form of the particular solution, and we would already know y1 and y2 from the homogeneous case, so we would use this fact to help us define these function multiples of our homogeneous solutions. Okay, so what do we have here? If I take the derivative of this, I have the product rule, right? So this is the product rule of this portion, and this is the product rule from this portion, right? So u2 prime y2 plus y2 prime u2, right, for this portion. I take the second derivative. So basically we're just gonna, like we did before for undetermined coefficients, we're gonna find these derivatives and plug it back into our equation, right? So I find my second derivative, so I'm doing the product rule 4 more times, and I get this result. So again, hopefully you guys are watching this with a pencil and paper. There's a lot of algebra, a lot of calculus on this section, but we're going to formulate some really easy formulas. So it'll take us a while to get there. So make sure that you guys are writing all of this down. I'll try to go slow so you guys have time to sort of write these things down as we go through them, right? So again, I'm doing the product rule here. Okay, product rule for this one are these two terms. Product rule for this term gives me this, and the product rule here gives me this here, right? So I have my y prime for the particular solution, the second derivative of my particular form, and I'm going to plug these back in. Okay, so obviously this is a very long equation. If you notice, I have two terms in the middle here that are the same. These two edges are not the same, right? This u2 is the second derivative. Here y2 is the double derivative. And this 4 and this 4 are pretty much the same, except for these are subscript 1, these are subscripts 2, right? But if you notice these two terms here, these are identical, right? These are identical. So that's like terms that we can combine. I can get my, so it looks like a perfect square, almost, right? If we're trying to compare these to polynomials, right? So these first 3 terms and then these last 3 terms, right? So that helps it a little bit, but still me taking this whole thing and plugging it for y double prime and this whole thing for y prime and then this for y prime, it's going to get very long. So I wasn't able to condense it down into one single line for each of these steps. Most of them are. I could have, but the font would have gotten really small. So just bear with me. I did try to break these down in pieces as best as possible though. Okay. So when I substitute these back in, right? So y double prime plus p of x times y prime plus qx times y equals g of x. I'm going to plug it back in. This implies, right? So my dE implies to me that I can plug in my y double prime. Okay, so that's just this line all over again. Okay, plus p of x times y prime p of x times my y prime, and then I will add just my yp, okay, times q of x, and all of that. So again, this is the short form without the x's in here, right, for this, and all of that will equal g of x, right? So I'll take a second so you can rewrite this. So all you're doing is rewriting the stuff that we had before. There's not really any math, it's just a substitution into this equation, okay? So what I'm going to do now is I'm going to try to rearrange things as best as I can, okay? I need to simplify this down. Honestly, me subbing in p of x everywhere and q of x everywhere here is not going to be super helpful. So what I'm going to do is I'm going to form this y double prime, y prime, and y times p of x and q of x for my y1 and for my y2. So if you notice, I can pull out a u1 here because I have a p of x times y1 prime. I have a p of x times y2 prime, and I also have a q of x times a y1, a q of x times a y2, I'm sorry, not y1 prime, but times the y1 portions. So so I can pull out a y1 form of this and a y2 form of this, and I know that y1 and y2 are solutions already, so I know if I were to take y1 and plug it into this equation, it'll equal 0. I know if I take y2 and I plug it into this equation, I'll get 0. Okay, so that's what I'm going to do. I'm going to move stuff around just a little bit. So I'm factoring out u1. Okay, u1 here for the y prime. I have u1 for a y1 double prime. So I'm taking this term, I'm taking p of x times this term, and then q of x times this term. All of those have a u1 in front. u1, u1, y double prime 1, y prime 1, y1, right? So double prime, prime, no primes, and that's times the q, the p, and this, and all of those had the same u1 in front. That same thing goes for the u2 because again, there's just a lot of symmetry going in this equation, right? So I can take u1 and pull it out of these terms here. I can group these together and pull out u2. So again, I'm plugging my y1 into this, right? And y2 into this. And I'm not plugging it in, I'm just taking what I have already and I'm moving stuff around, right? So I know this is going to be 0 and this is going to be 0. And what I have left over, okay, so again, this is all one line. These two lines here is one line of math. So if you're doing it on your own paper and you have room, there should be one line. So I'm pulling it out this. I got this going up for me here because I know that those are going to go away. And then this is what I have left. So I have the y double prime y1. This is left over. This is left over. And the u double prime 2. And then the stuff that's left over with the p of x. Okay. So just to clean this up, I'm taking these two lines here. Okay. And I'm pulling out the u1s. Basically, I'm taking all the stuff that has just u1 without it being factored, and I'm grouping it together, right? So this is the only thing that has a u1 that's not a prime, a u1, a u1. Everything else is u1 prime or double prime, okay, or u2. So I took all the u1 stuff and I grouped it together. I took all the u2 stuff, right, all the u2 stuff, and I grouped those together, and that's how I got this first line, okay? All the stuff that's left over is just what's left over here, okay? So on this next line, I know that this is going to be 0 because I know that y1 is a solution to the homogeneous portion. So if I plug y1 in, this is 0. If I plug in y2, this also goes to 0. So I know that these two facts are true. So that means this whole line right here plus this line, that part of my equation goes to 0, and I'm going to be left with just this thing right here. Okay, just this is going to be left over. u1 double prime, a u2 double prime, the things that have both primes mixed in, two of them, because remember we had to add them together, and then what's left over with the p of x, all the q of x stuff is gone, and of course g of x is still there. Okay, so this is the stuff that's left. Okay, that first half of the equation is gone because these two things are 0 when I plug them into my equation. Right, so this is what I have left over, and this is what I'm going to work with. Okay, so the first thing that I'm going to do here is I'm going to split these apart. Okay, I know I added them together. I'm going to unadd them. Okay, I'm just going to split these back into u1 prime, y1 prime, plus another one of itself. Okay, so I took this and I split it here. Right, so here's the other one, and I took this one and I split it twice also. Right, so I grouped one of them together and I just threw the other one just before the p. Same thing here. I took this one and I kept it with its pair, the u prime 2 y2s, u double prime 2 y2s. I kept that together. I switched this a little bit, so if you notice they kind of match up, these two, and then this is the one that's left over from here, and this is the one that's left over from here. So I split it into pieces and I regrouped them so that I can do my next step. Okay, everything else over here is the same. And so when I come to the next step, what I notice is that just these two terms and these two terms, which is why I paired them together after I split them, this is a product rule, right? So just like when we do the integrating factor in the first order equations, if I undo the product rule here, right, then I get u2 prime times y2. And when I take that derivative, I would do the product rule and I would get this as a result, right? So what I'm doing is I'm undoing product rule for this, undoing product rule for this, and this is the stuff that's left over. Okay, so again, I'm taking this stuff and I'm undoing the derivative. I'm not doing an integral yet, I'm just writing the equality, right? If I were to do the derivative of this, I would get u1 double prime times y1 plus u1 prime times y1 prime, right? The product rule. Same thing here. This is the product rule. I'm just undoing the product rule, bringing myself backwards. Okay, so my next step, okay, the next thing that I get to do, I'm really just working over here. This stuff is going to stay the same on this line. We know that if I'm taking the derivative of two things and adding them together, I can just say I'm taking the derivative of one thing. So think about a polynomial. If I have a 3-term polynomial and I differentiate it, I'm differentiating the first term, I'm differentiating the second term, I'm differentiating the third term. That's kind of what this looks like. I'm differentiating one term and I'm differentiating the second term. So I can kind of factor out this derivative. So again, I'm not doing an integral per se, but I am undoing, I'm using the equality properties of differentiation in order to kind of get myself to a result. Okay, so I can pull out this d dx and I have u1 prime y1 plus this thing here. So if I were to differentiate this, again, just think about going backwards. If I were to start here, I would have to differentiate this thing and add to that the derivative of this if I were to differentiate this, right? So that's what I'm doing. Okay, so if you notice, now I have p of x times this part. So what I did was I just took this and I took this and I swapped positions. So I put this one in front and I took these two and I put it right here. So again, as I go through the math, I'm just moving stuff around. Okay, so now what I'm going to do is I'm basically going to assume that this u1 prime y1 plus u2 prime y2, let's assume this is 0. If I assume that this is 0, I have some function of x times 0, which is going to give me 0. And if you notice, what I have here is exactly the same. What's inside this parentheses is exactly what's in this parentheses. So if this ends up being 0, 0 times the function is 0, the derivative of 0 is 0. This goes away and this goes away, and I'll be left with this thing equals g of x. So notice this is not the same as this. Both of these are differentiated. u2 prime, y2 prime, u1 prime, u1 prime, y1 prime. These are, both terms are prime here. Here's just one. Okay, and it's the same one for both of these. So if I allow this term to be 0, this goes away, and this is equal to g of x. Right? So assume that this is 0. Then this whole thing goes to 0 because I'm taking the derivative of 0, and I have 0 times a function. So that whole thing is just 0 plus 0, so that's 0. And what's left over is an equation. Okay? So taking those assumptions that this is 0 and that this is what's left over, I have a system now. Okay? A system of two equations and basically two unknowns. Those unknowns being u1 and u2, because y1 and y2 I should know from my homogeneous equation, right? So I need to solve this for u1 prime and u2 prime. Okay, so let's go through that again. So my linear algebra students, you can use whatever method you know to solve this. Those of you who have not taken linear algebra, we'll just go through and we'll work this the regular algebra way, right? So my goal is to basically eliminate something. I want to either eliminate these two or I want to eliminate these two. So what I'm going to do here is I'm multiplying this equation by y1 and this by y1 prime. Basically, I'm trying to eliminate this set of terms here by making them equal, right? If I multiply this by y1, I have u1 prime, y1 prime, y1, and this will be u1 prime, y1, y1 prime. Okay, so I'm getting these equal so I can just subtract the two equations and get this equation out of the way. Okay, so I get these two to be equal, right? So it goes away. They're identical terms. So then I get this term minus this term, and that will be minus gxy1, right? And so again, I'm trying to solve for u1 prime or u2 prime, but if you notice, u2 is the only thing that is around. Okay, so what I can do is I can factor this out and then take what's left over and divide it over to the other side. So if I take out the u2, I'm left with y2 y1 prime minus y2 prime y1, and I can divide that, and then if I change the order, I make it negative and I can get rid of this negative sign. Okay, so that's what I do. I divide by this bottom. So if you notice, the y2 y1 prime is on this side because I'm just switching the order. If I switch the order, I can take the negative and I can get those two negative signs to cancel out and keep this negative in the middle. So that's really all I did, was I just moved stuff around so I can factor out a negative sign and get those negatives to cancel. So this is what u2 prime will look like. Okay, it is written only in terms of the things that I know. My given solutions, y1 and y2, their derivatives, and that g of x function that is on the end of my equation, right? So y1 and y2 are given to me, so I have those equations, their derivatives, and the formula function for g of x, right? So that's what my solution is written out of. Okay, u2 prime. So that's how I would find u2 prime. That works all the time, right? So now let's do the same thing for u1. So I'm going to take the same equation, but instead of multiplying it by these things to get rid of these terms, I'm going to get rid of this term so that I can solve for the u1 prime instead. Okay, so I'm going to multiply by y2 prime and y2 so that these two terms are identical, because the only thing missing from here is a y2 prime, and what's missing from here is a y2, so that's what I'm using. So I can subtract these two, get them to go away, and then I have this thing minus this thing minus this gxy2. So again, same thing like last time, almost identical. I have u1 prime minus u1 prime. That's a factor I can pull out, and then I can move these to the other side by dividing. Notice I cannot get rid of the negative sign here because my answer here, this order, matches the order I have for u2 prime. Okay, so I get the order to match up, which is nice because once I find this once, I don't have to do anything weird. I just have that value. Okay, so it's the same exact order, same exact value, right? So another important thing is note that the Wronskian of y1 and y2 is the determinant of y1, y2, and then the next line being their derivatives. And so I'm just taking the determinants. Remember, it's this subtracted by this product. Okay, so y1, y2 prime minus y2, y prime prime, y1 prime, y2. Okay, and if you notice, that is the exact value of what I have down here. y2 prime, y1, y2 prime, y1, minus y2, y1 prime, minus y2, y1 prime. Okay, so this denominator in u1 prime and u2 prime is just the Wronskian of the two functions that you're already given, or that you found from the homogeneous equation, right? So I can rewrite u2 prime as g of x times y1 divided by the Wronskian of y1, y2. Okay. Similarly, u1 prime is g of x times y2 negative, right, divided by the Wronskian as well. Right, so that Wronskian is super important. And so remember what we had all the way in the beginning. My idea for the solution, for the particular solution, is some function times y1 and some function times y2. That's how I form this particular solution. So now that I have the derivatives of u1 and u2, I need to integrate those things, right? So u1 is the integral of g of x times y2 over the Wronskian, and y2 is the same thing. That it's going to be the integral of this with respect to x or t, whatever the variable is. Okay, and my actual solution is y1 times this plus y2 times this u2. Right. So my particular solution is u1 y1 plus u2 y2, or this formula. Okay, so this will work for variation of parameters for all of our problems, right? We can just plug it into this formula. A lot of work to get there. So again, you don't want to memorize the steps to getting here, but you do want to understand how this was formed, because when we try to work with higher order cases, it works the same way. And if you notice, I only gave you for a second order, right? If you run across a third, fourth, or fifth order equation, you're gonna have to kind of extrapolate that information yourself, right? So let's start an example. Right, so we have a second order equation here. This is my g of x function. In order to start this, I need to find the solutions to the auxiliary equation. I need to figure out my homogeneous general solution, right? So very easy equation, m squared minus 2m plus 1. It's m minus 1 squared equals 0, right? So then that means my solutions are a double root, m equals 1 and m equals 1. So then my general solution is c1 e to the x plus c2 x e to the x. Remember, we're bumping it up by power of x every time we have a repeated root to keep these things linearly independent from each other, right? So I need to now find the Wronskian for my function, okay, my y1 and y2, right? So if we come back to my thing, my solution is dependent on my Wronskian for both of my u1s and u2s. So that should be the first thing that I find, right? Again, everything else is given to me. G of x, I know. Y2, I know now. Y1, I know now. I just don't have the Wronskian. So I'm going to take my two solutions to my general solution, my auxiliary equation, and I'm going to find the Wronskian of those. So e to the x, its derivative, x e to the x, its derivative. I multiply these two, and then I subtract the product of these two. So this is e to the 2x plus x e to the 2x minus x e to the 2x. Okay, e to the 2x plus x e to the 2x minus x e to the 2x, and then of course you can see that these two cancel and I just get this thing, and that is not 0. Okay, obviously if it was 0, we really just couldn't continue on with our equation. There's just no solution, right? They would not be linearly independent from each other. Okay, I would have probably messed up somewhere, to be honest. So I have e to the 2x. Okay, it's never 0, so I don't have to worry about the interval of existence or uniqueness or anything like that either. So now I can start to throw these into my equations, right, for my particular solution, since I already have my general. Okay, so the first one is y1 u1. So that whole first portion, okay, again, u1 y1 is y1 times the u1. So that's that's this part. I need this whole thing and I need this whole thing. Okay, so when I throw it in, this is the let's see, y1 is dependent on y2, right? So y1 times the Wronskian times g of x times y2. Okay, so as we start to simplify this, you can notice that I have an e to the x times another e to the x here, which is e to the 2x. I already have that on the bottom, so that gets to cancel out. So I got negative e to the x times the integral of x over 1 plus x squared. You can do a u sub here, right? We're not going over techniques of integration anymore. We've done a lot of integration, and that's calculus 2 stuff. So you can do a u sub here, and you should get out negative 1/2 e to the x natural log 1 plus x squared. Okay, again, it might take you a little bit long to do that by hand, but your sub would be u is x squared, then du is 2x, and then you move that over, so you got that x there, and yada yada yada. Okay, so that's my value for y1 u1. I don't have to do anything else. I don't need to put the C3, C4s or anything like that. That's all. It's all taken care of. Okay. My y2 u2, I do the same thing. So I put y1, y2 here. I have y1 times g of x. So again, you notice e to the x times e to the x is going to give me e to the 2x on top and this on bottom, so it cancels, and I'm left with this. There should be a dx here. I guess that got away from me in my code. If I do this integral, there's no x on top, so I'm not going to get another natural log. This is actually tan inverse, so I get sorry, oh man, I messed up a lot. This should be x e to the x, x e to the x. This is tan inverse, so this is my final answer. Okay, I'll make sure in your script that this is right. So at least there's less mistakes this time. That's good. So this is my answer for y2 u2. So this plus this is my particular solution plus my general solution gives me this as my answer. Okay, so it was a lot more work to derive the formulas than to actually solve, right? So if we started here, I solve the auxiliary equation. I take the Wronskian of the independent solutions that are in the general solution, and then I just plug all that stuff into my formulas, and I do two integrals. I put them together, and that's it. Okay. If I had initial conditions, I would apply the initial conditions to my final y, right? And that's what I want you to do for your classwork. This is a classwork, not an extra credit problem. Again, I'm going to alternate between extra credit and classwork. So I hope you guys have been doing the classwork because these are regular mandatory, although extra credit is good because that's extra credit, right? So I will post the due date, or the due date will be tonight at midnight for this classwork, and then I'll post the solutions the day after, so you guys can check your work and have enough time to use that as an extra reference for completing your homework that is on WebAssign. All right, have a good one, guys. I hope you're not getting too stir crazy. You know, I've been working a lot myself, but I'm extremely bored. So hopefully you guys are doing okay. I think what I'm going to do this week is I'm going to try to schedule some Zoom office hour times for you guys, so you guys can kind of check in. I haven't been able to get my camera to work for Zoom, so you can't see my face, so I don't know. It works on my phone, but it doesn't work on my laptop, so I'll try to figure it out for you guys. In case you guys have any questions, you can ask me directly, okay? Enjoy the rest of your break. After this week is spring break, so I know we can't go anywhere, but at least you won't have to do any work, or you can use that to catch up or whatever it is you need to do. All right? See you guys later.